What we'll be looking at now is the second part of simple harmonic motion with some specifics. We're going to relate them to two different things, pendulums and springs. And with a spring, okay, you got to remember, what do we need to have? We have to be able to oscillate back and forth, okay, past some type of equilibrium position. This equilibrium is a resting position, okay? So if we had a ceiling here and then, a little string and then our spring, and then we could put a little weight on here, right? At rest, that's the equilibrium position, okay? Now what we'll end up doing is you can pull this down a little bit, okay, and release it, and then so one cycle is going to be an up and a down, okay? So the time for one up and down, right, is going to be what? The time for one complete motion is the period, okay? But you got to remember, we're going to go back and forth around some, there's your equilibrium position right there. Mathematically, you look at this with something called Hooke's law, which is talking about the relationship of the restoring force to a spring constant and a distance. That's the distance from equilibrium, okay? That's the displacement. So if we had our other spring that I just drew, right, there's my spring and here's the weight coming off of it, right? Your equilibrium is at rest, okay? When you pull this down to some distance, that is your x. That's a displacement from equilibrium, okay? So that force, basically here, that force is going to be your weight, is directly proportional to this thing called a spring constant and the displacement from equilibrium. The spring constant is specific to each type of spring, okay? The period of that spring, and this kind of looks like it got off track just a little bit, the period of this spring is equal to 2 times pi times the square root of the mass on the spring divided by the spring constant. Okay? Does that make sense? So the time for one complete motion is 2 times pi times the square root of m over k. Okay? And if you've been in, here's a sine curve. If you've been in, I don't know if you get into them in Algebra 2 or not, but I know you do in pre-cal, you get into the mathematics of this type of a sine curve. Your mass will be in kilograms, your spring constant will be in Newton meters. The other thing we'll look at is pendulum. Okay? Remember, what does a pendulum got to do? You got a back and forth motion. Okay? The pendulum period is the time for one complete motion. Okay? So it has some type of equilibrium position at rest. You pull it back, let it go, but it's a complete back and forth motion. You can also relate this to energy if you remember back, right? Because when you pull it back, it has potential energy, and at the bottom it has kinetic. So the period of this pendulum is the time for one complete back and forth motion. This period is the equation's just a little bit different. Okay? The period of that pendulum is 2 pi times the length of the pendulum divided by the acceleration due to gravity. Okay? So what's that going to be? There's our old buddy, 9.8 meters per second squared. Okay? The mass has no effect on the period of that pendulum. The length of that pendulum is what determines the period. Okay? And again, if we were to graph this out, we would get a sine wave looking thing as well. That's all we need. We'll talk to you later. Bye.